let's start with Euler's fantastic connection between different dimensional attributes of geometry. Okay, so that's pretty good for vertices. Oops. CES. We're going to have E for edges, and we're going to have F for faces. Now, what do these things have in common, or how do they differ? Vertices are very specifically zero-dimensional. Edges, line segments, they have length. That's it. So they're one-dimensional. And faces are two-dimensional, right? They're areas. Okay, well, you can imagine continuing this, perhaps. What Euler did is he noticed that if you take, well, we'll generalize it later. If you take a sphere and you subdivide it in some way, it turns out in any way, right? You can make any different way of breaking up the sphere, the surface of the sphere, into different combinations of vertices, edges, and faces. Well, then when you do, if you take all the vertices and add them up and write down the number of vertices, and then subtract the number of edges, and then add the number of faces, you always get 2. This is now known as Euler characteristic. Okay, turns out anything that's homeomorphic to a sphere. So you can stretch it, and well, you can't pinch. There's the rules what you can't do, but you can stretch it as long as you keep the basic general form. But if you get a hole, then now you move to a different kind of form. It would be like a torus and so on. But for anything homeomorphic, so any kind of stretching of the sphere you want is still homeomorphic to a sphere, and then you subdivide it, you're going to find this. In particular, if you take any of the Platonic solids and put them inside of a sphere and use them to subdivide the surface of the sphere, you'll find that their Euler characteristic is 2. What does this mean? They have a dimensional built-in relationship that's fixed between the numbers of their individually dimensional features. Really beautiful. And keep in mind, this is a relationship that's built in for anything that's subdividing the sphere. Now we're talking about a model of the universe that's on the outside a giant sphere. And then it is subdivided, right? So we're interested in the logic of how it gets subdivided. Okay, next step. Next step is to write down the equation for that outside sphere. This is our infinite hyperbolic construction that's applying to an infinite sphere. So we have an infinite sphere that's dividing internally hyperbolically, okay? So that perhaps a bit of a fiction because you can't get all the way to infinity, but geometrically we're allowing all the way to infinity. And if we did, it's under this hyperbolic construction specifically, what roots does it have? Well, it turns out the solutions to this, or its roots, because it's set to equal to 0, are the imaginary golden ratio, 1 over the imaginary golden ratio, the imaginary golden ratio squared, and 1 over the imaginary golden ratio squared. You notice a repeat. All of them are composed of the imaginary golden ratio in a slightly different way.
Very neat.
And in total there's 6. 1 here on the denominator, 2 here, 2 here in the denominator, a total of 6 of them arranged as roots to this infinite hyperbolic construction. That's what we're imagining. What is the features of these roots that we usually care about in algebra? If we want to take the sum of the roots, so if we take their sum, add all these together, equals 0.
Yeah.
If we take the product, equals 1. And if we take the quadrants,
it's -1.
-2.
Oh, correct.
-2. So the picture we have in our mind here is this is representing a hyperbolic internal division construction of an infinite sphere. So it's like the infinite hyperbolic construction. Okay, so we have these features of this infinite sphere, right? Its roots have these combined features. Now, the thing of interest here is that we have a -2 and we have a 2. We know how to interpret this 2, right? What does it mean?
It's a dimensional conglomeration. No, it's basically just
Yeah.
the person minus the edges plus
It's a built-in rule attached to anything homeomorphic to a sphere, okay? Any way to decompose a sphere, so, or anything close to a sphere, homeomorphic to a sphere. Okay, so we're decomposing a sphere with this rule, and here we're saying we have a projected sphere that's being decomposed by the infinite hyperbolic construction with its quadrants is -2. Exact opposite of that. Okay, another interesting way to go. Euler also pointed out that if you take x to the k minus 1 equals 0, these simple forms of polynomials, right? So we're talking about factorizations now. We're going to take the simplest kind of polynomials. You can start out with x to the k equals 1. Move the 1 over so that we're looking for roots here. Okay. This always, no matter what we put in for k, okay, k can be 1, 2, 3, 4, it can be also negative. This always gives us, or always has solutions of the form cosine of 2 pi n over k plus I sine 2 pi n over k. These are the roots, these are the solutions to any simple factorization structure of a polynomial like this. Okay? Now, if we put a simple restriction on that, meaning pick roots, pick a set of symmetries that we care about. What do I mean by that?
So we can tell a story from.
If you pick k is equal to 4, your roots are going to be, we're on the unit circle, starting here. It's going to be right here, 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 and here. Right? It's going to be the roots of unity, and how many of them there are depends on the value of k. So if we pick k is equal to 6, then they're going to be here, 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 and here. There'll be 6 of them spread around the circle. Well, that's exactly what we want to do, both of those cases actually, because we have a structure that we're saying at the base is maintained entirely as, this is the equation, the first bit is I, and I was a rotation of by 4 symmetry operator, and dilogarithm of 1 over the imaginary golden ratio. And an imaginary golden ratio, again, -1 to the 1/3, while I is equal to -1 to the 1/2. Okay, that's half the story minus the other half, also with an argument of the imaginary golden ratio. So these two roots, right, this is the inside structure. These are the same roots that we're using to make the outside structure, at least while we're interpreting it as an infinite structure. Then all we have to do is wrap some of its internal boundaries on themselves to quantize it and change the story. But at this point, just thinking of the infinite sphere that's being divided, we've got an internal structure, an external structure, and now let's restrict to 4 and 6. This is 6-fold symmetry, this is 4-fold symmetry, right? I takes 4 times to go around the circle. The imaginary golden ratio takes exactly 6 times to go around the circle, right? So in fact, I can just write it like this. I to the 4th equals 1, and the imaginary golden ratio to the 6th equals 1. Okay, so because of this in our structure, in our geometric structure, we have this rotational symmetry built in. So let's make the assumption that there's a factorization polynomial, and let's guess it's simple, something like this, okay? But then we're going to restrict it exactly to 4 and to 6. Okay, so if that's our restriction, first let's do 4. What do we get? 2 pi times k is 4, so this is going to be 2 over 4, so it'll be pi over 2 times n. Okay, so we're going to get cosine of, I'll write n times pi over 2. That's in the case where k is equal to 4. And on this side, we're going to get plus I times sine of same thing. Let's do a different restriction. Let's now take over here, let's pretend we took k is equal to 6. What changes? 2 pi divided by 6 becomes pi over 3. So now we go to cosine of n times pi over 3 plus I times sine of pi over 3. Oops, I missed the n. N times pi over 3. Great. So these are the two kinds of roots we care about now. If we've already got a reason to restrict our system, our factorizing system, to rotations that are 4-fold and 6-fold symmetric. Okay? Okay, well, let's take these pieces now and ask, what happens if we want to take all n? Just give me all of these and give me all of these. Give me all of these and give me all of these. Meaning, let's take a total sum. Let's go on for this one. We're going to take a sum from n equals 1 to infinity of cosine n pi over 2. Okay, and that is equal to, I'll write it over here, 4 squared. Okay, what about if we take sine of all the n's of pi over 2? So rewrite it now. We're going to take the total set from n equals 1 to infinity of sine of n pi over 2. And that's going to be the Catalan constant, which I'm going to represent with a k. It's got other representations inconsistently in even same places, but the Catalan constant. Okay. This might feel a little bit dry, nothing you've recognized maybe if you don't know what the Catalan constant is yet. Maybe you've heard of Catalan numbers, right? But this structure, 4 pi squared over gamma 5, 1 over 32, is probably quite suggestive, at least to you at this point, right? Cool thing here, you can do one tweak on this, or over there, you can take the alternating sum, right?
Yeah.
When we take the alternating sum, what happens?
We're missing the k over. It should be all over k squared. Or
good call. Thank you. Thank you.
No, I did not. That
N squared.
off. I wasn't sure if we're going in a
Thank
different
you.
direction.
Thank you. You're right. Absolutely. Over n squared. You're right. So we're not taking just all of these roots. We're taking all of those roots and assuming that they're under square balance. Okay, that's another assumption. But we're doing that because we know these geometric pieces, right? We have answers to what these pieces are. And we notice not just that we're getting sphere under hyperbolic decomposition or the Catalan constant, related to the entire Catalan structure of numbers, but when we come over here and change it to pi over 3 instead of pi over 2, we're doing the exact same thing now. We're going to write the sum from n equals 1 to infinity of cosine n pi over 3. Now it equals, sorry, I almost missed it again, 4 pi over gamma of 5 squared. And when we take the other one, n equals 1. This is the punchline 1. So if you held in this long, here's your reward. Pi over 3 equals the Giesking constant. Okay, and this is the one we're most interested in. Thank you. Thank you. I just keep missing that, huh? Okay, in each case we're dividing it by n squared. Did I miss any? No, got them all. Okay, this is the one we're most interested in. We've identified directly as the minimum manifold, right? So if you want a minimum possible cycle of any kind, this is the limit in geometry on which you can be tracing that cycle. Let's say that again. If you want the minimum possible closed cycle, this is the limit, this is the shape on which you have to be tracing the boundary of that cycle. Okay, so we really like this structure, but now when we see in here, we have a way to see it in other construction, right? From other angles. It's the same exact construction here, but what did we change? Here, it's the other half. These two halves come together. They're both in pi over 3. But if we put in the argument pi over 2, then we get the Catalan constant, or this.
But the other interesting thing is we did find what trivially did look like connection to the figure 8 knot and the Giesking manifold. Right about 7 significant digits, there was a deviation. That was unexpected and interesting.
That one was for the tangent, right? I have it actually for the alternating tangent, but maybe it was for the tangent also. No. Okay, for the tangent, it's 4/3 the Giesking constant, and for the alternating tangent, so the same sequence, but you put a -1 to the n in front instead of, imagine before we had a 1 to the n. It's just the 1 always stays a 1, so it never showed up. All it's changing is the sign of every other entry goes negative. Okay, so the alternating sequence gives you exactly, that's the point I guess for you, is saying it's not exactly. It gives us minus VFE, but to 8 significant digits. Now, the stuff we've been saying here before were to all digits, right? This is a very curious thing. In fact, it won't tell you what it equals. It doesn't bring this value up because it doesn't equal it to all digits, right? If you back off, you get this as an approximation to it. That's very interesting. Why would it that when we're in sine, we get the Giesking manifold, but in the tangent, we get the double of it almost? Anyway, we're going to look for that surge, or we're going to look for that piece, and hopefully that can tell us a little bit more of the story in terms of factors, right? We're looking for factorization, but we're really wanting more than just how many factors, what's simple relationships between factors. We want the shape of the factors. We want to understand the actual geometric boundary that things are factoring on. So we would need the number of pieces, but also the shape along which the factoring is happening. Okay, so that's our goal for some bits of clarity we're after. But right now, we can notice that the story of factorizations in polynomials themselves seem set up already in a way that's foundationally arranged around the Giesking constant, right?
Yeah.
That's just a cool thing to notice. So the mystery that everyone can feel that there's hidden in this, the magic that this is even true, right, is perhaps connecting to the mystery of how spheres are being divided, and the fact that the universe we live in and all of its manifest and built-in inherent properties and rules and so on are literally coming from an inherent structure that's factoring along this geometry that we're now slowly teasing apart piece by piece. Anyway, this is the insight. We have a geometry where we do assume that we have a fourfold symmetry built in and a sixfold symmetric symmetry built in. So under both of those, if we collect those roots, we get already as one of our limits by collecting the roots, the Giesking manifold. So this is another way, I guess, to look at the structure. But when we do, we get a little bit more than we're getting here. Of course, there were other ways we've talked about before of looking into this structure too. But this way, by collecting all the roots to get there, we can easily just change the parameters and see what do we get then and get a related relationship. In fact, these are both related because we have I in here and that in the same picture. So the pi over 2 and the pi over 3, both players in this game. One more thing. I think I briefly mentioned before that if we take the alternating series of these, or this one, then we get something interesting also. So let's write that down here. This time we're going to take n equals 1 to infinity. But instead of having 1 to the n there, which I didn't write because it's just 1 the whole time, I'm going to take negative 1 to the n. So it's going to be the alternating version of the same thing. Okay, and all the effect of this is literally it just takes spits out the same sequence of numbers, right? The exact same construction, just changes the sign every other one. Okay, well now this time, when it was the full sequence, or I should say the base sequence, we get the Catalan constant. And when it's the alternating sequence of the same construction, we get beautifully minus the Catalan constant. Now, this is a symmetry that's shown up here that's fantastically beautiful. Why? Because you obviously can use that piece to cancel with the other one. There's lots of things you can do with this, but there's another place in math, super famous place in math, where we have a series of sums of something, right, that has a very interesting inversion also. In fact, the other inversion, this one's what kind of inversion? We go from positive to negative, positive to negative. The other kind of inversion in math would be from on the numerator to the denominator. Okay, so what is that one? We have a sum n equals 0 to infinity of 1 over n factorial, right? This is first few elements are 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial and so on. But as you get more and more, the denominator gets smaller and smaller, so the contribution gets less and less, and you converge into something, and the number you converge on when you take all possible inverse factorizations is E. Now, let's write its alternating sum. It's going to be now negative 1 to the n over n factorial. See, before here I could have said 1 to the n. Maybe that's more symmetric. So put it in if you want. Now, the second entry is going to be minus 1 over 1 factorial, plus 1 over 2 factorial, minus 1 over 3 factorial, plus, now when I say dot, 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 you're supposed to assume and keep in track that we're plus, minus every time. So this is very similar to this one, right? This is just the alternating sum version of this sum. And what do we get when we take this one? We can't get E. You're not going to get the same number.
You get 1 over E.
We get 1 over E. This is a beautiful symmetry to pay attention to. And the exact same beauty of symmetry, but in the different form, is showing up here. We get an inversion, and all we did was take the alternating series versus the series. It's a beautiful base of hyperbolic structure to begin with. But we're going to let that hang on the cliff, and hopefully it's enough to warrant further investigation by any curious minds. But that's the connection I wanted to bring forth today. So.